Hello, everyone. I'm Zhiming. I'm doing a postdoc with Dr. Yongming Liu at Arizona State University. Today, I will talk about the knowledge discovery of nonlinear dynamical system. In this work, we developed a PDE learning method to improve the robustness of physics discovery. This is the outline of my presentation today. Given a certain dynamical system, usually there are two problems to be solved. First, with sufficient knowledge about the system, we can characterize the system using a physical model represented by an ordinary differential equation or partial differential equation. Then the system behaviors and characteristics can be simulated by numerically solving this system. Unlike this forward problem, the second problem is an inverse problem. Given sufficient data measured or simulated from the system, can we accurately discover the underlying physics? Obviously, the inverse problem is more challenging than the forward problem, especially for a novel system that we have very limited knowledge about. So what is the benefit of attacking such a challenging problem? This brings up the power of knowledge discovery. I'd like to give an example using the COVID-19, probably the hottest topic in the past 1.5 years. Since its outbreak, there have been almost 2,000 studies modeling the spread of COVID-19. For example, our colleague at Arizona State University developed this equation set to describe the spread of COVID-19 in the counties of Arizona. This model is validated by comparing with the analysis results from the CDC. Following that, this model is used to analyze the effects of some control measure, such as the face covering on the spread of COVID, which is also proved to be efficient. So knowledge discovery or equation discovery help us to establish an advanced understanding about the system. For example, what is the driving force of the system? What factors are trivial for the system? Additionally, with the discovered equations characterizing the system control, as well as the diagnosis and prognosis becomes more straightforward and efficient than the case without a physics model. So what is the state of art of PDE learning? Sparse regression is the most widely used type of methods in the literature. For a certain dynamical system with this general form, the objective of PDE learning is to construct the expression on the right-hand side given measured data. Upon discretization, the time derivative can be expressed as a product of the library matrix theta and the coefficient vector Kc. This column of the library theta corresponds to a specific candidate term for the governing equation. A key assumption is that the function on the right-hand side consists of only a few terms, making it a sparse functional form. As a result, there should be only a limited number of non-zero elements in the vector Kc. Therefore, this problem can be solved through linear regression with a regularization term that penalizes the model complexity. A fundamental limitation of existing sparse regression methods is that there's no ground truth for tuning the hyperparameter lambda. We have no idea about the correct model form behind the data. Therefore, how sparse is a big issue in PDE learning. PDE learning is different from traditional curve fitting problem. In curve fitting, a model is efficient as long as it has sufficient fitting accuracy and it generalizes well to the new data. In PDE learning, we're quite picky about the learned terms in the equation. For the example of the Berg's equation, the model becomes a lot more complex with these higher order terms and more challenging to analyze and control, even though its coefficient is quite small. Therefore, in this study, we propose a new method to improve the robustness of PDE learning. It is called the progressive and sparse identification of PDEs, or in short, the Cypd method. This method starts from the noise measurements represented by the red curve. First, the data is denoised through neural network modeling by splitting the data into training and validation sets and setting early stopping. Then the denoised data is used to calculate the numerical derivatives and formulate the library matrix. Following that, the first Fourier transform is implemented to transform the problem from the temporal spatial domain to the frequency domain. In this process, the high frequency components are excluded because they are more susceptible to the noise components. In this study, we developed a novel algorithm for sparse regression. That is the Psi algorithm. In the Psi algorithm, the least square regression is adopted to avoid hyperparameter tuning. The importance of each candidate term in the library is progressively evaluated using the regression accuracy. Additionally, we allow more than one solution of sparse regression in case it's hard to determine which term is more important than the rest of terms. Finally, we evaluated the representativeness of each candidate solution from sparse regression by solving and optimizing its model form, taking the measured data as the ground truth. And finally, determine which model we should eventually end up with. Next, I will explain the last two steps in more detail, taking the Burke's equation as an example. The Burke's equation is used to characterize a displacive system. For this Burke's equation, the library is built using the spatial derivatives and polynomials. The importance of each term is evaluated by solving this least square regression problem. In the beginning, the matrix theta is set as the initial prescribed library. The importance of each term is evaluated by removing each term sequentially and comparing the regression accuracy. It shows that the system is the most important because removing it ends up with the largest regression error. Then we update theta with the sixth term and evaluate the importance of the other terms by adding them sequentially to theta. It shows that these four terms have a very close contribution to the regression performance. For model simplicity, we won't proceed with these two very complex terms, and we don't want to make a hard decision between these two terms by balancing the model complexity and the regression accuracy. As mentioned above, we allow more than one candidate solution in the Psi algorithm. As a result, we end up with 3 candidate models. Finally, we evaluate the representativeness of each candidate model. For scenario 1 with these two terms, this is the initial model obtained from sparse regression, and this is the model, the optimized model. This figure shows that the solution of the optimized model matches very well with the simulated data from the ground truth PDE, and the difference is quite small in the whole domain. These are the results in scenario 2. It shows that the difference between the solution of the optimized model and data is very large, especially around the region x equals 0. In scenario 3, we have 3 terms in the model. It shows that the difference between this, the model solution and the simulated data is pretty much the same with that in scenario 1, which means that adding this complex term to the model does not significantly improve the representativeness of the model. Additionally, we found that after optimization, the coefficient of this term becomes almost 10 times smaller. Therefore, we can conclude that this complex term is trivial for this system and finalize the solution at the optimized model in scenario 1. So what are the merits of the Cypd method in PDE learning compared with the other methods? First, the influence from memory to noise is largely reduced through neural network denoising and a faster Fourier transform with frequency cutoff. Most importantly, we won't fall into the realm of hyperparameter tuning, since no hyperparameter is introduced in this method. Last but not least, the robustness of the learned model is guaranteed by solving and optimizing all the candidate models and evaluating their representativeness. Next, I will present the results of PDE learning for several candidate dynamical systems using the Cypd method. I will start from the dissipative system characterized by the Burke's equation. These are the results of PDE learning for this system with data containing different levels of noise. It shows that the correct model form can be discovered using the Cypd method even with data containing as much as 50% noise. The second system investigated in this study is the traveling wave system, characterized by the KDV equation. Again, the correct model form can be identified with data containing as much as 50% noise. This figure compares the solution of the ground truth PDE, the learned PDE, and the simulated data with 50% noise. It shows that with the Cypd method, we are discovering the underlying physics instead of overfitting the noise components with complex terms. Another system investigated in this study is the system characterized by the 2D Brooks equation. It shows that we can correctly identify the PDEs using data containing as much as 40% noise. The last system we investigated is the layer-driven cavity flow, characterized by the 2D Navier-Stokes equation. Again, we can successfully identify the correct PDE form using data containing as much as 50% noise. Here's a quick summary of this research. In this study, we developed the Cypd method. It can be used for robust identification of PDEs from noise environments. Thank you so much for your attention. This work is supported by NASA. All the materials can be found on these websites.